Okay, all right. So what I wanted to do, we have like about 40 minutes. So what I wanted to do quickly, is to go over, two things which will kind of set the stage for what we want to do from next time on. One is to kind of just do the mean field theory of this simple Ising model, which, probably most of you have seen, but, hopefully I'll go over it quickly to just, set the stage, and then we'll kind of jump to Landau theory and kind of discuss some basic aspects and then continue with Landau theory in the next lecture. So let's, can people in the back see if I write about this much? Okay. So let's, define the Ising model again, right? And we will use mean field theory to kind of discuss some aspects of the physics that we want to capture and then switch to doing Landau theory. So the Ising model, as I mentioned on the slides earlier, and hopefully many of you have seen it, is a model where I have a classical a problem where I have a Hamiltonian where I start with some spins labeled by sigma I, which are plus or minus 1, which interact, and let's say in this case, they interact on neighboring sites, I and j. And they are, let's say, in the presence of a uniform magnetic field. Actually, this need not even be uniform. So let's just keep it. Yeah, let me keep it. Let's assume it's uniform for now, and I'll look at a non-uniform case in a second. Okay, otherwise, this would be hi sigma I inside the summation. Okay. And now you say, well, I want to solve for the thermodynamics of the system to learn about its properties. And the first step would be in a statistical mechanics calculation would be to calculate the partition function, which is the trace of the exponential of minus beta h, which is the thermal density matrix, right? And in this particular example, the trace just means I should sum over all the classical configurations of these spins. So there's just sum over all the spins at each side taking on many values. So there's like 2 to the n configurations here, where n is the number of spins in the problem. Right? And once I have this, then I can take this log of this, gives me the, the temperature, gives me the free energy, and I can then start calculating thermodynamic observations. Right? And if you want to calculate this, you would say, well, this is a complicated problem, which, as we'll see, you can do this in 1 dimension, and, Onsager did this in 2 dimensions exactly. But for now, we'll kind of simplify the problem and use this kind of mean field approach. And the mean field approach, actually, how far down can people see in the back? I mean, I can certainly try about this much. Okay. So maybe I should start writing from a little higher. So a mean field theory says that, well, I don't want to kind of do this complicated sum over a huge number of degrees of freedom. This is complicated, so I'm going to simplify this problem by kind of replacing this interactions by something that looks like a single spin problem, which I can solve exactly, right? And so you say, well, I can try and rewrite this Hamiltonian where I think of this by just adding and subtracting certain averages. I can replace this by saying, well, I can replace the sigma I by its average value acting on sigma j plus sigma I sigma j bar, okay, minus h sum over I. Sorry about that chalk. And we're just going to rewrite this in a way that you can check that this identity works, but let me just do it carefully. So I've just added and subtracted certain things involving these averages. So this now is the thermodynamic average at site I of the spin. Similarly, this is a thermodynamic average at site J. And this in general, and we'll see in certain cases, these need not all be, uniform in space, but for the simple cases that we'll look at translationally invariant solutions. But this is an identity. I mean, I've not done anything here. I've just added and subtracted certain things to make it look like I have changed the problem slightly. Okay. And so now what we can do is, so this sigma I, sigma j is still here. That's what this original interaction is. Things like sigma I bar, sigma j will cancel between here and here. So it's really, I've just, okay. So now we can do two things, right? So once we have it in this form, you can say, well, imagine I have a system where I have a site which has a huge number of neighbors surrounding it. Then it would be justified to replace the influence of everything that's around me by its mean value, right? So crudely, this is like doing central limit theorem, where if you have a large number of random variables, you add it all up and you get something that's close to the average, right? And so you can say, well, maybe I'm justified in a certain sense in dropping quantities like this, where since the spin will not deviate from its average value. Okay. And so if you drop these things here, this we can drop because it's a constant. It's going to change the energy by some number, but that's not going to change observables. It will turn out to be important for certain things, but let's not bother about it for now. Then this problem you see just reduces to a problem of spins at sites which are independent, spins at each side that are seeing some magnetic field. Right? And the magnetic field in this case, for example, at site I, so let me write down the Hamiltonian for the entire system, the rest of it, right? This part here. This part of it, I can rewrite in the form where it is just a problem of that the ith spin is going to see a magnetic field that's coming from this external field, but it's also going to see the magnetic field coming from the interaction with all the neighbors, right? And so this J here sums over all the neighbors of I. Okay. And so what you see is that the mean field Hamiltonian looks like just a single spin in a magnetic field at each site. Okay. And so for this one, I can very easily write down what the so this is like some HI effective acting on sigma, multiplying sigma I. And now I can work out what the partition function is for that spin. Right? And so it's just, I should just sum over up and down. So I'm going to get a partition function that looks like e to the beta h effective at site I, right, plus e to the minus beta h effective site I, sorry, I. For the two values of the spin, it's just e to the minus beta times this Hamiltonian, sigma is plus or minus 1. And so this just becomes 2 times the hyperbolic cosine of beta hi. And from this, you can kind of work out what your mean field, your overall free energy is going to be minus temperature times the log of the partition function. But in this particular case, the partition function is independent at each site, right? And so what you get is that if you take the log, you end up getting a logarithm of this 2 times cosine hyperbolic of beta hi effect. Okay. And now what I have to do is I want to try and calculate from here the magnetization of the system. And I want to make sure that the magnetization of the system that I get from here is kind of the same as the magnetization that I inserted into the problem. In other words, it's a self-consistent calculation where I start by assuming a certain average or a certain magnetization. I use that assumption to calculate an effective one-site partition function from which I get the total free energy. From this free energy, we're going to calculate the magnetization by taking derivatives with respect to not H effective, but with respect to H, right? And then I should kind of equate that magnetization to the sigma I bar that I started with in the first place, right? So that kind of gives us a closed loop. And so if you now kind of calculate what is Mi in this picture, this is just sigma I bar, right? But another way to calculate it is by taking derivatives of the free energy. And so that gives us an equation, and I'm going to write this out here, which is just which is just a tan hyperbolic function. By taking derivatives, I have to take derivative with respect to HI effective, and then take derivative of HI effective with respect to H. Okay. And so this number, you can kind of work this out, is beta H plus beta J times, sorry. So this gives us now an equation that I can solve self-consistently for the magnetization at a given site, right? So I start by, I could kind of imagine calculating this iteratively, start by inserting some magnetization here at some given field, temperature and field are given to me. You stick in some magnetization, calculate this, go back here, you get all the MIs. Then you stick in all the MIs back here, and you kind of imagine kind of iterating over this to get the magnetization. Okay. And this we can do in several different versions. So let's imagine we do this first in the case where we assume that things are translationally invariant. So let's imagine I have Mi, which is the same at all sites. Okay. Then this equation tells us that my magnetization is going to be tan hyperbolic of beta H plus beta J times M times a sum over all the neighbors of site I, but that's the coordination number. Okay. So this will give me beta times J, and let me call the coordination number little z times M. Okay. And so this is a simple equation that you have to solve iteratively in order to calculate what the magnetization is. Okay. So this is like an equation of state, like the equation of van der Waals equation of state. This is some version of an equation of state for the system where you give me temperature, you give me the field, and I'll work out what the magnetization is, right? And if you do this at as a function of, let's say, fix H equal to 0, okay, then you can try and solve this problem, graphically, where you say that, I can plot the left-hand side and right-hand side, and I want to demand that these two are equal, and those will give me my solutions. The left-hand side is just M, right? So if I plot the left-hand side, is just going to be a straight line. This is my left-hand side versus M. Okay. It doesn't depend on temperature. Sorry, maybe that doesn't look like slope 1, but it's supposed to be. Okay. If I draw the right-hand side as a function of M, then it does depend on temperature. So if I'm at very high temperature, then this function looks something like this. It's eventually going to go to 1, but at sufficiently large values of the magnetization, eventually it will saturate the tan hyperbolic. Okay. But if I am at large values of beta or at low temperatures, then this function is going to look sharper. So it's going to start off like this, and it's going to give me something that goes between -1 and +1 much more sharply as I tune the magnetization. Right? And so you go from a situation where I have to equate this right-hand side at, let's say, high temperature. This is the right-hand side at low temperature. Okay. And so at high temperature, if I want to equate the right-hand side and left-hand side, there's only one solution, which is M equal to 0. Right? And if I want to do this at low temperature, you find that there are new solutions which appear. which other than m equal to 0 correspond to two magnetizations which correspond to these crossing points. Okay, and so this is an example where, which is the analog of the van der Waals, where we went from, having a single root to the problem where you have three roots to the problem. Okay, and so in fact, the physical roots which actually have a lowest possible free energy turn out to be these magnetizations here. Okay, so these are values of the magnetization. Let's call it m naught, and this is minus m naught, and it depends on temperature. Okay, and so you can solve this problem, and what you end up with in mean field theory is a problem where you can plot this magnetization as a function of temperature, and you see that there is a certain TC at which these three roots first appear, right? Where I'm going to exactly have this line meeting this line such that the slopes kind of match down here. Then you'll get, a triple root in some sense to this equation, exactly like in the van der Waals critical point. Okay, and this TC turns out to be just the coordination number times J. So that's an energy scale. Okay, and as you lower temperature, this magnetization increases and eventually goes to 1. Okay. That's if the magnetization is positive, right? But there's also a solution where the magnetization is negative, right? So you could equally well have ended up with a solution where the magnetization does this below TC. So I could also end up with a solution where the magnetization goes to -1. So this is what mean field theory tells us. It tells us that there is an existence of a phase transition. Below this temperature, the magnetization becomes non-zero, but it's equally likely to be up or down. Okay, and the way I'm going to select between these two is to, have like a small field, let's say the Earth's magnetic field in a real setting with like an extremely tiny field, and that will allow us to pick one or the other solution. So I'm going to randomly pick either this solution or that solution, depending on some tiny microscopic perturbations that might be present in the real system. We'll kind of select between these two, but otherwise, I have no way of telling whether the system should have positive magnetization or negative magnetization. Okay. If the system has no such perturbations, in fact, it will break up into domains. There'll be regions which will want to be +1, other regions which will want to be -1. Is this fine? Okay, so this is one thing that we get from here. But you can kind of try and kind of understand the physics in the vicinity of this transition more clearly by saying, well, I can try and expand out this tan hyperbolic, assuming h is 0 and m is small, which is what it is here. I can try and expand this equation of state and powers of magnetization. Okay, and so what you see from here is that near TC, I'll assume that m is much, much less than 1. And let me assume that h is 0. Okay. If that's the case, I can take this equation of state and write it as m is approximately given by the expansion of the tan hyperbolic function. And so that gives me something that's beta j z times m. That's the first term. And the second term in the expansion gives me something which I should kind of make sure I don't get it. Ah. Okay. Do people remember the next expansion term? What's the factor here? Sorry, I don't seem to have written this down. I think it's some 3 or 1/3 or something. Sorry. So 1/3. Okay, let's go with this and see where it fixes. Okay, if it's wrong, we'll fix it. Sorry. Okay. Fine. Sorry, I should have written it down everything, all factors carefully. Okay, so this is what we end up with. And now you can say, well, I can try and solve for this equation. So now it's a cubic equation, right? And I clearly have one root, which is m equal to 0, okay, which is this root here, which you have to check that this actually has a higher free energy than the other two roots, which appear at non-zero magnetization. And the other two roots, you can say, well, I can cancel off this m here. So what I'll end up with is 1 is roughly beta jz. But remember that jz is in fact Tc. Okay, so I'm going to trade this microscopic quantity here for the transition temperature itself. So I'm going to write this as Tc divided by temperature times m. So this is kind of in the spirit of this van der Waals way of trading microscopic unknowns, in this case, J for something that you know, which is the measured Tc, right? Plus 1/3 Tc by T times, sorry, there's no M here, right? So then you realize that, okay, I can solve for M now. This is just a quadratic equation. So this gives me that M is approximately 3 times √3, sorry, square root 3 times plus or minus square root 3 times 1 minus Tc by T. What did I do here? Minus 1/3, sorry. Thank you. And in the limit that T is close to Tc, so that I'm kind of very close to this region in the phase diagram, then you find that the magnetization has a specific form where it has plus or minus, so that's consistent with having two solutions, right? But it grows in a very specific way as I lower temperature. In other words, once temperature hits Tc or goes above Tc, it's 0. Once T is less than Tc, it has this characteristic behavior that goes like the square root of, how far I am from this critical temperature. Yeah. Okay. So this tells us we can actually work out, solutions where, for how the magnetization behaves. But we can do more than this. So this is kind of the behavior of the magnetization in the vicinity of this point. Of course, if you want to solve the full nonlinear problem, you can kind of get this full curve numerically. Okay, but this is what we can get in the vicinity of the transition point. But there are other things you can calculate from here. Okay, and in particular, we can kind of look at the regime where you calculate what's called the spin susceptibility. Where what you want to get is the value of the magnetization at small non-zero magnetic fields, and then calculate a linear response. In other words, if the magnetization is proportional to the applied magnetic field, what's that proportionality constant? Okay. So we want to get some equation that looks like the magnetization at small fields must be proportional to the applied field. At zero field, the magnetization is 0. And let's say I'm here, somewhere here at high temperatures. But when I apply a small field, the magnetization becomes non-zero. Okay. If that's the case, then we expect on general grounds that maybe the response to leading order will be linear in the perturbation that I apply. Okay. And so we want to get an equation of this sort. And again, we can try and do this in the regime where we say, well, h is small, m is small. And let me expand this just to linear order for a second in the value of this variable here. Right. So then we'll say, oh, well, if we want to do that, then the equation of state gives me that m is approximately beta h plus beta jzm, but that's really Tc over T times m, right? And now I can solve this linear equation, and I find that m here is given by beta h divided by 1 minus Tc divided by temperature, which is just h divided by T minus Tc. And we're doing this in the regime where temperature is greater than Tc. Okay. And so now if you do this, you see that, oh, the response of the system is obtained by taking a derivative of this magnetization with respect to h, dm dh. And this quantity is just 1 over T minus Tc. So this tells us that at high temperatures, the susceptibility is small when temperature is very large. Okay. You apply a small field, there'll be a very tiny response. Okay. But when the temperature gets closer and closer to Tc, this response is going to diverge in the system. Okay. So this tells us that if we plot chi as a function of temperature, it's going to diverge at Tc. Okay, and this is one way to see why somehow the system must spontaneously magnetize. In other words, if the system is becoming unstable, eventually it will spontaneously form some magnetization when you go below this point here. Okay. So these leads us to kind of things where you say, well, I can try and look at this. The way this response appears always seems to be some ratio of T divided by Tc. Similarly here, if I factor out Tc, then this looks like something where I can write it in terms of T over Tc minus 1, right? So this quantity here is proportional to 1 over T by Tc minus 1. This looks like some other thing, which is temperature divided by transition temperature, with some, 1 minus this raised to the power half. So you see that in all these cases, what I've done is you can kind of trade quantities that are like things like J for Tc completely in this examples of this sort. Okay. And the other thing you find is that the behavior is singular in the sense non-analytic in the vicinity of this transition. In other words, it starts off being 0 and then suddenly becomes square root. It's not some smooth function as you cool the system down. It's not a smooth function. Okay. So this allows us to define the behavior near these phase transitions can be defined in terms of now what you might call these reduced temperatures. So temperature divided by Tc, just like in van der Waals theory, we had pressure divided by Pc and temperature divided by Tc. Here I have these combinations which appear that kind of dictate my behavior of the susceptibility or the behavior of the magnetization. Okay. So let me kind of write out what this looks like, right? So in this particular case, we found that the magnetization goes like 1 minus the reduced temperature. Sorry, I wanted to, so the distance to the critical point, let me actually define my as a reduced temperature. Okay, so I want to measure it such that T equal to 0 corresponds to the temperature being equal to the transition temperature, but suitably normalized so that I don't want to make any reference to my microscopic coupling. Okay. Then this magnetization scales like this reduced temperature T to the power of 1/2 in this particular case. And you can put in sort of factors if you want. You can kind of work out what exactly this is. So this has some factors of √3 and so on and hanging out in front from there. But basically you can rewrite it as a form, which is this, normalized reduced temperature raised to the power of 1/2. Similarly, the susceptibility in this case goes like 1 over the reduced temperature. So this goes like 1 over T for T bigger than 0 or T to the minus 1. And you can work out a whole host of other thermodynamic observables, which I have not kind of done here, but let me just write out a bunch of other things which I had this, I wanted. So there's also something else you can work out is the nonlinear magnetization. So imagine I'm sitting at T equal to Tc. So my temperature is equal to J times Z. We can work out what the magnetization behaves as a function of field. And in this case, it turns out that it's a nonlinear function. So this is when T is precisely equal to 0. So temperature equal to Tc. So you're sitting now not here where the response was linear in the field, but at this unstable point, and you're trying to apply a little field and asking what the magnetization is. And here the response is not linear. It's a nonlinear function. And so here you find that the magnetization scales like 1/3 power of the applied field that you have. Right? So in other words, if you take a derivative of m with respect to h to calculate the susceptibility, it will diverge in the limit of small fields. It'll go like h to the minus 2/3, and that's going to diverge as h goes to 0. So what you see is that this critical point here is characterized by things which behave in singular fashion, the magnetization, the susceptibility, this nonlinear magnetization. Okay. And all of them exhibit sort of singular behavior near Tc. And by singular, I don't mean it diverges. I just mean it's not some smooth analytic function as you tune temperature of fields. It's not some smooth analytic function. Moreover, you find that the behavior is not, this behavior is in the form where it depends on the variable that you're tuning, in this case, temperature, the distance to the critical point, raised to some power rather than, let's say, exponential of the temperature or some weird behavior. It actually falls in the form where it behaves as some kind of power of the field or a power of the temperature. Okay. So you see that it's singular and it exhibits what are called power law behavior. So you can, corresponding to these, you can say, well, what is the power or what is this exponent here? I can kind of define a set of exponents corresponding to the behavior of each of these thermodynamic quantities. So more generally, we would say, well, this quantity should go like mod T to some power beta. So this defines a certain critical exponent. It tells us that if I'm in the vicinity of this magnetic critical point, in this particular case, I have found that beta is 1/2. And maybe more generally, beta could be something other than a half, and we'll see what it can be. But in general, it goes as some temperature to some power. Similarly, this susceptibility is expected to go like mod T to some other exponent minus gamma. So it's going to diverge at the critical point. This power is gamma equal to 1 in the example that we have, but in general, maybe it's not equal to 1. Right? Similarly, the magnetization, this nonlinear magnetization is some mod h times, of course, some, I have to put in some sign for h here to the power of some 1 over delta. And in this particular case, delta is equal to 3, but maybe it's not equal to 3 more generally. So what we find from mean field theory is that thermodynamic observables that we have behave in singular fashion. We see that there is a symmetry breaking phase transition, and there is a very specific form of singular behavior of these observables. Okay, and what one wants to do is to ask whether these kinds of behaviors can be captured within some framework where I don't have to appeal to the microscopic description by trying to do sort of mean field theory on a specific lattice with specific interactions. Can I kind of coarse grain the system and get rid of this detailed information to some degree and kind of write the problem in terms of some order parameter degrees of freedom. Actually, do people have any questions at this point, or? Yeah. Sorry, yeah. So this is for T. You can generalize. I mean, of course, M for in this case, M is 0 for T greater than TC. In this case, the susceptibility, you can also write it for T less than 0. It also behaves like 1 over mod T in that case. Yeah. But is this fine? Have people seen mean field theory before for the Ising model? Or sorry, I should have kind of, it's unclear sort of what the, yeah. By? Correct.
How do you by if you're getting inspired by the fact that the field is the power to, then we should be able to justify that field is somewhat right near the regime.
Right. So in general, we don't know when, right? So from here, the way we've kind of justified mean field theory in this particular case is to say that really it works, provided I can make the assumption that the field coming from all my neighbors or the effect of a neighboring spin can be replaced by its average, right? Or the magnetized, right? And so that really works provided in some sense you have a large number of neighbors. So a given spin sees many neighbors, right? And you would say, well, I'm using some kind of central limit like theorem where I'm saying if I have a large number of neighbors, then its effect on the central spin that I'm interested in can be replaced by an average environment. Okay. So strictly speaking, this would seem to make sense only if the number of neighbors goes to infinity. Right. So it would seem that this, does it only work? So I could ask, does mean field theory only work when the dimension or the coordination number or the dimension of my system, does it go to infinity? Maybe this is a sense in which mean field theory, as I've done it, strictly applies, right? We'll see that this is not quite true. It's certainly true that it works in large dimension, but it turns out that qualitatively, the behavior near this, near the transition actually works provided you're in high enough dimensions. Okay. And in this particular case, in this case of the ising model, it works provided you're in dimensions that is bigger than 4. Okay. So it looks weird because there's nothing in anything that we have done tells us that 4 is some special dimension or anything of that sort. I've just assumed that large number of neighbors such that there is an average environment. And strictly speaking, that would only make sense provided I can use the central limit theorem provided I have a large enough number of members. So in the limit that D goes to infinity, this should be strictly true. Right. But in the vicinity of the critical point, it turns out that the physics remains true provided you're in high enough dimensions. Okay. Actually, can I take 5 minutes extra or what is the, okay. So let me do that. So what I really want to do is to say, well, I want to try and step away from, taking a specific model and working out specific behavior and phase diagram to asking, can I try and replace this by trying to think in terms of degrees of freedom, which are not individual spins and trying to kind of work out what they do on a lattice, but try to formulate the problem slightly different. Okay. And so to formulate this problem slightly differently, so what's called sort of Landau or Landau-Ginzburg theory. Right. Is you can try and say, well, I don't want to calculate the partition function the way I did here. I want to try to do it in a slightly different way, where I say, well, I'm going to still start with this picture that I want to add over all spin configurations of e to the minus beta h, where h could be anything. It could be the Ising model Hamiltonian, maybe it's some more general Hamiltonian. including, let's say, further neighbor interactions or something. But I don't want to do it in one shot using mean field theory. I want to do it in a slightly different way where I want to take my system, which is defined on the lattice, right? But I'm going to break it up into little chunks where I say, well, I have this little chunk here. I have another chunk, which is, let's say they're all the same size. I have this little chunk in my system. I'm going to try and break it up into these little blocks. Okay. And I'm going to calculate this sum somehow in 2 steps. Okay. So the first thing I'm going to do is I'm going to define within each chunk some magnetization. And let me call I now as labeling the chunk here, not individual sites. Let me use a different thing. Let me call it R to distinguish it from the lattice site. Let's say R is kind of labeling my block. Okay. I'm going to say that this block has, I can divide it just like, if I have 2 particles, I have like a center of mass and a difference degree of freedom. I can say, well, I'm going to replace the effect of all these spins by its average and then all the fluctuating sort of individual spins in there. Okay. So this is for all I that are part of this block, sigma I, that's what this is, right? But if I hold this fixed, I can still sort of have a lot of fluctuations in these individual spins. Is that fine? Right. So we are going to evaluate the sum in 2 steps. You're going to say, well, let me evaluate the sum by first assuming that I'm going to have a certain value for the magnetization in each block. Then I'm going to calculate a constrained sum, where I'm going to sum over all the configurations within each block, subject to the constraint that their magnetization, the total magnetization is MR. So let me just write it at this way, right? Just for simplicity, there's a constrained sum, where I'm going to sum over all these with a certain fixed magnetization. Okay. Now, of course, it's not very clear that I can constrain the magnetization. The spins inside can do whatever they want, because of course I can take a spin and it can flip by 1. So the magnetization will only change in certain steps. But provided this chunk is large enough, if I flip 1 spin, let's imagine that this magnetization kind of changes smoothly to some degree. Okay. So we'll go make that assumption in a second, but I can kind of break up this partition function calculation by doing it in 2 steps rather than in 1 step in mean field theory. Right. So this is still e to the minus beta h. I've not done anything yet. Okay. But now I'm going to say, imagine I do this particular summation first. Okay. I want to say, well, imagine I could do this summation where I'm going to replace this by taking a certain block and then doing this over all the blocks in my problem. Right. So let's, okay, I don't know, let me write it more clearly. So let's kind of imagine that this is a sum over all blocks, sum h of block. This is all the interactions that are within this block, right? Times some e to the minus beta times h, some boundary. And this is a schematic. So, we are not going to do this calculation, right? But I'm going to break it up into a sum of sort of everything that's inside this block. Those are all things in the Hamiltonian, this bond, that bond, all of that will appear here. And then there are things which sort of connect me from one block to the next, which are kind of appearing as what I might call sort of boundary-like terms here. Okay. And then crudely, what I'm going to assume is that this thing here, when we do the summation, what I'm going to get to, if I ignore the boundary terms entirely, right, then this calculation becomes a calculation over disconnected blocks. Imagine I slice off all these bonds. It just becomes a sum over individual blocks. And this quantity here is simply the partition function of a block subject to the fact that it should have a certain magnetization M. Right? So let me call that partition function free energy, but let's put like a twiddle. It's not the thermodynamic free energy. It's the free energy of the block subject to the fact that this block should have a certain magnetization. So that's like a constraint on, the block free energy is like it's constrained to have a certain magnetization. And now I should kind of sum over all the blocks in the problem. Is this fine? Okay, so you'd say, well, this looks like a problem that I can kind of solve because, I just have to take, so imagine I could diagonalize like a 6x6 cluster of spins. I could try and calculate what this free energy is subject to a certain magnetization, right? And now we can try and ask, well, this sum over M of R, right? We'll say, well, if this block is large enough, then the magnetization can change kind of smoothly. It's not changing in jumps. I don't have to worry about the fact that this magnetization can only change in jumps. Let me assume that I can, vary it smoothly. Then from here, we can go to something where I replace the sum by an integral. Over all possible magnetization fields defined on this coarse lattice. So it's as if I'm going to zoom out such that each of these, think of it like a point, and this magnetization, that magnetization, all of them, I'm going to integrate over some smooth functions involving the magnetization. This free energy here, let me replace this entire thing by, we can call this an action if we want in the language of field theory. This would be like you give me a magnetization profile, I'll give you a certain beta times free energy of blocks. Let's call that an action. Okay. So what you're going to get is something where, I have some action, which is a function of M of R, functional of M of R. Okay? So you give me an entire function, and I'm going to spit out one number for you. Okay. So if we do it like this, we realize that there is now I can use a slightly different picture to calculate my partition function. And we'll kind of turn to this in the next lecture. Sorry, it'll just take a couple more minutes and I'm done. Right. So what we want to do now is to ask, well, what is this function S? Yeah, sorry. We will bring it back in just a second. Okay. So I have neglected it for now. Okay. But imagine I neglect it completely, right? Then you'd say, well, what is the form of this S of M of R? And you say, well, I have to do some microscopic calculation, right? But you can ask, well, imagine I don't want to do microscopics. I want to try and guess at the form of what this could possibly be, right? So S of M of R, what is the possible form that this could take? Right. So first of all, I have to integrate over all space or sum over all R. So I'm going to imagine that I can replace that by an integral over all space points, right? Which is I'm summing over all of these, but let's assume it's smooth. Okay. So you can ask, well, what is the form that this is going to take? So this would take the form where I can now say that, well, look, in each block, I'm calculating the partition function of some finite system. This is going to be some nice smooth function of parameters like the magnetization. Okay, it's going to be a nice analytic function of the magnetization. There's nothing singular or there are no phase transitions. If I take like a small block, I'm not going to see any phase transitions. Okay, if that's the case, I can replace this S of M of R by saying I'm going to just tailor it in powers of M. Okay, so there'll be a zeroth part, which is S of 0, no magnetization. If M is 0, then I'm going to call it S0, right? If M is not 0, right, I want to ask, does my block free energy know about M being positive versus M being negative? And because the Hamiltonian has time reversal symmetry, there's no difference between M being plus and M being minus. There is no difference in the energy of the free energy, right? And so you conclude that the lowest order term that I can get is something that is proportional to, let me just call these coefficients some ABC for now, okay? The lowest order term is going to be something proportional to M square. And now you say, well, if I keep going on with the Taylor expansion, what else can I get? Can I get m cube? And you say, no, I can't get m cube because of it's odd again in under time reversal. I can get m4, I can get m6, and so on. Okay. So on general grounds, we expect that when you calculate this constrained free energy and Taylor expand it, it will have a part that's here, which is the zeroth magnetization equal to 0, and then there'll be corrections. At least for small magnetization, there'll be corrections which can be Taylor expanded in powers of m. Sorry. Yeah, so if there is a magnetic field, I'll stick it in later. Yeah, I'll put it in later. I have not put in any magnetic field, but it's easy to include it, and we'll do it at the end, and it's fine. Right? The magnetic field only couples to the net magnetization, so I can just do it at the end. So if you want to add a magnetization, it'll look like plus integral or minus with my notation, some h of r, m of r. And that's fine. If it's uniform, you can pull it out of the integral, but otherwise it's just some spatially vacuum magnet. Okay. So you'd say, oh, that's what this free energy should look like. And so now my partition function, the zeroth order guess is my partition function should be written as e to the path integral, an integral over functions, in other words, of m of r, e to the minus this s, which is a functional of m of r. You give me a function, and I'm going to calculate this number, and I'm going to then add it up over all possible configurations of this field. Okay. And it turns out that this is not quite correct. And the reason it's not quite correct is exactly what was just asked, namely, how can I ignore these boundary terms? And really, I shouldn't be ignoring these boundary terms. And you can ask, well, what do these boundary terms do? If I reattach these couplings now, I can ask, well, what can it do at the level of this action here? What it can do is it can try and make sure that the magnetization on neighboring blocks does not want to abruptly change from being up to being down. Okay. And so what these boundary terms are going to produce for you are terms which will look in general, and I'm using some convention here, but these are just some prefactors. What it's going to try and do is it's going to try and prevent the magnetization from varying sharply over the scale of this particular block here. When I go from one block to the next, I want that anything which involves large gradients in the magnetization will be penalized. Okay. So what you expect is that there should be some coarse-grained description of the problem which does not involve knowledge of the microscopic Hamiltonian, okay, where I can absorb that into kind of this action, which is defined by a certain set of coefficients, okay, together with things which are called like stiffnesses that tell me that I don't want my order parameter to bend very much or change very much as I go from one block to the next. Okay, and so this is what the description is, which we'll kind of start using from next time. But the idea here is that we've gone away from site scale physics to some shorter length scale physics where we have coarse grained over some number of spins, where I've lost a little bit of the microscopic information, which eventually will reappear in knowledge of these coefficients. I mean, it's not like the microscopic physics is gone. It's buried in S0 and these coefficients. It's still there. And once I have that, then I've kind of traded the problem for something that's a little bit zoomed out. And now I can start using this to talk about the physics of the problem. Okay. And the reason to do this now is that you can say, well, I can try and do this kind of Landau theory calculation now for any problem with a local order parameter. Here I talked about spins, but if it was something else, like a fluid, I could have replaced it with a fluid density and try and written out something like this in terms of density fields. If there was something like a magnetization was a vector, I could have replaced this by a vector field and tried to do this. Okay. So what we'll do next time is kind of put this on a slightly better footing, and sort of not this process going from here to there, but really try and ask, given that the form of this Landau theory is this, what can we say about the physics of the problem? And then can we kind of improve what we learn from here to say something about the macroscopic behavior. Sorry, all these factors and so on, you'll have to fix. I think I got some of them wrong during when I was writing it out, but hopefully, I'll try and, make some neat notes. If people want later, I can post these notes. If there is a venue, I can post some. All right, so I'll stop here. Sorry for going over that.
Let's thank Arun then for nice lectures, and so you'll have another long way to go, 2 weeks, right?
Sorry.
So today is the first one, and he will have another, I think, 9 lectures.
Wow.
Okay. So also, let me just give you something.
History of RRI.
So,
Yeah, okay.